formula in the book. If you don't use the handy-dandy formula in the book, then you end up having to do it all by doing a regression getting different regression coefficients every time and making the fitted value. So you would have 25 pages of regression, right. 25 sets of regression coefficients. So
the y hat deleted I, is that what moves up into the position of your original I?
Y hat. I think I had an example last time where I had a regression equation, I had a picture like this, some data where the Anscombe's data, we can look at it, okay? If you want. This is without deleting the observation. Right? Now what happens when I delete it? I shouldn't have written over it because I think we did it over here. Suppose I delete that observation, which was the 9th observation here. X4 star is 40. This is the modified, that's why I call it X4 star. It was modified data, okay, from the original data set. Okay. If I now delete that observation, so copy this over. And now take this observation out. Move this data up. So it's a lot of work to do that. Delete those observations by hand. What did I do? Forgot to paste it. Whoops. Can't do that either. Actually, it's cut and paste. Yeah, you can just move it too. That's another way to do it. Yeah. There it is. Okay, now if I want to do the regression, here's the Y data. Here's the X data. Here's the label. Output range. Do I need the residuals? Not necessarily, but I do want predicted values probably, so I think that's what I'm going to put in. Output range right here. Okay. So here's your predicted values now it doesn't make actually that's not going to help me because that's giving me predicted for all the other points except this point. Okay. Now how do I get the predicted for that point? Okay, plug in these coefficients and the original 40 and 17.5 and the original 40. Okay, for X. So I take now. So what I would have, I can change all of these. Move these down, then I can give them new names. Why is it going through 11? Oh, I guess there were 12. Were there 12 observations in this business? Yes, there were. So I should call these 10, 11, and 12 now. Okay? And then for the 9th observation, what's going to be the predicted? Equals intercept plus 40 times slope equals 26.44059, okay? And the residual you would subtract you take equals to this minus the 17.5, right? Or 17.5 minus the other one. Let's put it the other way. Equals this minus this one here equals minus 8.9. Okay? That's the E sub I deleted. Okay? So E sub deleted 9 is equal to negative 8.94. Okay? And so on. Okay? So this says the actual predicted should be at 26 if I delete that observation. The other predicted was at I didn't put the predicted in there. Where is the other predicted? Did I eliminate it?
18.
Where was it?
Are you looking for the other residual output?
No, I'm looking for the other predicted. Yeah, the other residual output from the original regression.
Right.
Oh, here it is, 18.7. Okay. 18.7 versus 26. So if I take that point out, then it doesn't have as much leverage. So in other words, the line would move to actually, it wouldn't be bent down like this. Okay, it was bent down. I took the picture away. How do I move this thing up? Minimize it slightly. And I get rid of this page. Okay. Okay. How come I'm still getting stuff on the bottom? Okay. I guess I can't get it right the way I want it. I have to minimize it more. Okay. Okay. I had a picture here where this was the original data, and then I had a couple points over here, and this slope would have normally been going up, but this point up here was bending it down. Okay, so the least squares fit went like that, right, to the original data. Now the line, if I take this one out, okay, then the line's going to go up like this at a much higher slope. Okay, in fact, you can see the slope. The slope was 0.5, well, about 0.6 versus in the original one, 0.36. Okay? The 0.6 versus 0.36. Okay? So, anyway. So now, you can still estimate where the predicted would have been if I would have kept the point in. Right? So that's what y deleted I hat is. Okay? Y deleted I hat is beta 0 deleted I hat plus beta 1 deleted I hat times xi. Okay? Is that clear?
Yes.
Okay. The yi still exists. All right? Okay. That should settle it. But anyway, yeah, use the HIIs to calculate the breast statistic. Please. Okay. Sure. Please.
It's on the partial I guess just the language maybe, or I don't know. I don't know even know if I did it right.
Which partial regression?
Yeah, partial regression plot. I mean, when you say regress regress.
Y for x1 and
Yeah.
x2 for x1.
Yeah, I don't know if I did it right. I mean, I came up with some solutions that
Well, didn't I show you one of those too? Where did I show that one? Partial regression plots. Didn't I put one on here?
One example you have from another book. Your last name?
Computer repair times? No, that was not partial regression plot. I guess did I put it in the notes?
It is in the notes. You have that chart for us.
Okay, let's have a look at notes 5. I've gone, I can't remember what I did.
6.
Note 6.
Maybe it was notes 5.
Let's have a look. Note 6. Treatment of outliers, partial regression plots. No, it had to be notes 5. Which was the long one. Notes 5. Could I have a look? Yeah, I've done it, but now where to give you an example of it?
I can find one though.
I didn't do an example. I showed one in the book.
Yeah, there's one there.
You want to know how to do it? Okay. Let's go ahead and do one then. And what? Oh, let's see. You had to do it for problem 4. Okay, let's see if I can find one in here. I don't think I put it on your exam either. Okay? I don't believe I did. Did you get a copy of the exam now? Let's have a look. Here, the last two who came in didn't get the copy of the exam. Would you hand one back to her, please? Thank you. Let's have a look at how you do partial regression plots. I need to get... let's have a sheet that we've already had before. I need a 2-variable... Okay, let's have a look at let's have a look at 4.5, problem 4.5. Let's go ahead and look at the house data. Okay, I'm going to have to go find the house data. So let's go ahead and open up. How come it's not referring to the link? There we go. Okay. Okay. Let's see, the house data, which is problem 4.7 or appendix B9, I believe. Let's have a look. I got to make sure I have the right data. What appendix is that? House price data. It's property valuation data, which you're also going to have to use in your... Yeah. I'm looking for it in the appendix. Which appendix is it? No. Property valuation data, table B4, page 571. Problem 3.7. Problem 3.7 is referred to B4, I believe. The appendix B4. So I'm going to the data site. Okay. Problem 3.7. Consider the house price data in appendix table B4. Now let's just go ahead and look at it. Okay. B4. So I've gone to the data site, which you're going to have to also do. Okay, let's go ahead and pull that thing up. Okay, there it is. Okay, let's save it on the... property valuation. Okay, save it on the desktop. Okay. What do I have here? Is that what I wanted? That's what I want. I want to close this. Okay. All right, so what you have here is you've got the selling price of houses from some ancient house data, okay? Look, all the prices are between 29,000 and 40,000 or something like that. Okay, those were the good old days. Okay, but this is a very tight range of houses. Actually, maybe it goes down to 25,000. Okay, and what are the various variables? X1 is taxes. If you read on page 571. Let's just go have a look at this data a little bit. We'll prep you for your exam. Okay, X1 is taxes. X2, I should go ahead and maybe just stick that in there. Okay. X2 is baths. X3 is lot size, I believe. Okay. X4 is the living space, square feet. Okay. X5, number of garage stalls. And a lot of these are just numeric variables, either 0, 1, 2, like X6, or 1.5 in some cases for the number of baths. X6 was number of rooms. Then X7 was the number of bedrooms. X8 was age. And X9 was the number of fireplaces. Okay? Those are your variables. Okay, so 9 regressive variables, and then the selling price of the house in thousands. So, problem 4.5 asks, in part C or so, to do some partial regression plots. And there's a lot of partial regression plots. For each variable, there's a partial regression plot. For each regressive variable, so there are 9 partial regression plots. So what you want to do is you want to find the regressors, what is the residuals, with the variable deleted, okay? Okay, so we're going to have something like this. We have to calculate EY given, okay, then you're going to put in all the variables. Let's say, okay, let's do it for bedrooms after all the other stuff. Okay? So let's go X1, X2, bedrooms was X7. Okay, up to X6, and then skip X7, X8, X9. Okay. You've included all these. So these are the residuals, including all these variables. Okay? Then you have to calculate also EX7, given X1, X2, up to X6, X8, X9. Those are the notations. Is it pretty clear? Those are the residuals. And you plot one residual versus the other. Okay? That's the partial regression plot.
And that's all.
That's all there is to it.
Okay.
So you could do that, right?
I just wasn't sure that I understood that.
So that would indicate basically if that has a slope, that whether bedrooms are important after all those other variables, okay? Whether they should be included in the model after all those other ones. You would normally think bedrooms would be, but maybe not with all these other things in there, okay? We've already got rooms, fireplaces, and everything else, square feet. Maybe bedrooms actually is a function of those other things. If there's a linear dependence relationship, you might not need it at all. Okay, which turns out to be one of your related exam questions. Is there multicollinearity in the problem? Bedrooms may actually be a function, linear function, of rooms, taxes, and baths. Okay? Something like that. Nearly a linear function thereof. Or rooms might be, such a function. Should we just look at the partial regression plot just for the fun of it? Okay. So I've got to put beds over here to make it easier. I'm going to cut this column and put it somewhere else. Put it on the end. This is what I'd want to do. And then I just want to close this column. Okay? because I'm going to regress x7 on all the other regressors, and I'm also going to regress y on all these other ones. Okay? So let's do the regression of y and all the other ones. Input y range, there it is. Okay, input x range, all these other ones. What's going to happen? I did now. It says labels. I didn't put A1 in there?
Oh, you just did.
Y is the label, as long as that's okay. All right. Residuals, do I need any of that? Yes, I do. I need the residuals, okay? I don't need the residual plots, okay? I just need the residuals of this game, all right? And so output range, let's just stick it up here, okay? So what I'm interested in, there's all the coefficients. You're going to have to read that on your problem anyway. I'm going to skip looking at those. Here are the equals. These are the ones that I want. I'll give them a name. E, y, given all but x7. Okay? Okay? All right. That's the residuals that I want for the first. Now I guess I'll go over here and do the other one. Okay? Tools. Data analysis. Regression. Good. Y is the same. The X is... No, Y is not the same. I need the last column to be the Y's now. Okay? These X's are the same, actually. I could have saved that. Okay? Labels. Output range. I need to change that. Okay, over to here. Alright, so here are the EX7s. Okay? Given all other X, J. Okay? And so now I put those together. I want to plot one against the other one. So I want to put the y's on I want to put the residuals for the y on the vertical axis to see if I can capture the slope. Edit, copy, stick it over here. Did I get it pasted right? Okay, there's the residuals. Now I want to make a scatter plot of these two columns. Okay, there it is. Does it look any good? It looks like there's not much going on there. Okay, that's the partial regression plot.
And that's what we want it to look like.
Well, it depends what you want it to look like. I mean, can you see any formation in there? No. Which corresponds essentially to the fact that if I go up here, then if I look at the original regression, where did it go? Where is this? I don't have an original regression. I didn't do it here. Okay, so I need to look at the original regression. Whether beta 7 is significantly different from 0, given all the other ones. Right? That would be looking at a t-statistic for bets. Right? So if I go ahead and I better finish this chart so that I can just finish it up so that we can make a comparison. Okay, so this is partial regression. For added variable X7. Okay, beds. Alright. Y-axis E X7 given others. Other regressors. Value y-axis E Y given all regressors, excuse me, all xj except x7. Okay. Okay, now you've got that thing saved. Go down here somewhere. Okay. Okay, then I go back up and I see if that's consistent with the regression of all this stuff. Okay, what happened? Find a place to put it. Down here somewhere. Okay? Let's have a look at it. There's the standard error. There's the t-statistic. Negative 0.41. You'll see, though, if you look at all the t-statistics, practically none of them are significant. All the p-values are pretty big, except for the first couple. Okay? So that's part of the problem that you're going to encounter. Yeah?
When you do the chart part, do you grab all the y's first?
There's only one column of y's.
Right, you did the e to the y all but x7 versus
EX7 all but x1. So for the horizontal axis, I'm using residuals from regression of x7 on all the other regressors.
So then you got to highlight that first and then go to chart.
See, now how did I do it? Then I got the residuals out. Then I just put matched two residuals together. I cut and paste the residuals. I got EX7. Then I just cut and paste these other residuals over, okay, and moved them over next to so that I could just chart the pairs. Okay?
I missed that part.
Okay, sorry about that. Yeah. I cut these EYs, all but X7, and stuck them over here next to these. I just have to put the two columns together somewhere in this world and then chart it. Okay. Okay. I think we could save this now. And we can put it away. Okay. As long as we're in 107, we can look at that again. Okay. This is a real room problem, let me tell you. Switching rooms, switching computers, switching point of view. All right, that handles the partial regression plot, I hope, since I didn't have an example. You get kind of fast with Excel here after a while. You just get a little annoyed. You have to cut and paste so much. But,
well, I tried to do that yi minus y hat. Try that one, 32.
yeah, that could take a while.
And I wasn't doing parts of it.
Yeah, so you really want these. Now you know the handy-dandy computing formulas in the book. Somebody got a paper out of that. Or at least a short paper, perhaps, at one time. Just computing things like that. Yeah. Okay. Why don't we go on then, unless there are further questions about Chapter 4, studying the residuals. You're going to have plenty of review on your test, so I assume that people are going to ask about this on sometime this week, the test, or you could ask about it on Monday. It's not due till next Wednesday. We are going to meet on the 3rd of July for a while, anyway. Okay? For as long as we need to. There shouldn't be too much traffic on the roads. So, if you don't want to show up on the 3rd of July, please read the exam and ask questions. Maybe everybody would do each other a favor and do a little bit of that in case there's questions, clarifications about the exam. Okay. Okay. So let's go ahead, and what we're going to do is go to another chapter today. Okay. Chapter 4 was a little bit long, but Chapter 5 isn't that long, but there's a lot of worksheets to go through, a lot of examples. And the main problem is what happens if some of the model assumptions are not valid. Okay. And mainly, the thing we're going to look at today is the constancy of variance assumption. What if the variance is not constant? You saw some examples of how that might happen in those pictures of the residuals in Chapter 4, where they showed you the double bow and the funnel and whatnot. Those pictures on page 142. They showed you the ideal situation for the residuals in which the model assumptions are satisfied. Then in two cases where the variance wasn't constant, and then a third case where it's clear that their variance maybe was constant, but the regression function was wrong. This was all pictures for simple linear regression, just to highlight the problems that might arise. Okay, is everybody going to follow that? Variance not constant in these two diagonal pictures. So what we want to do is have a look at some examples of how you could correct for that. What's going to happen is, well, how do you correct? I mean, if the variance not constant is the variance not constant, right? So what can you do? Well, it turns out in some cases you can transform y, or you can transform x, or you can transform both x and y. Okay. To get the standard assumptions. Then, of course, if you transform y, you have to pay for it a little bit. Okay. How do you interpret the answers and so on? So what you're going to get is you're going to get to a situation where, probably it's best to illustrate with an example, but you get to a situation where with the transform model, the variance constancy of variance is holding. Okay, you get some least squares estimators. You try to transform. You can transform back then to the original units, the original model. Okay, and what you have is then perhaps slightly biased estimate. It wouldn't be biased, but well, yeah. You get perhaps biased estimators, but they're more stable. Okay, they have smaller variabilities. Okay, we're not going to talk about how to get rid of the bias. Here, the author gives a paragraph saying, well, refer to this, that, and the other if you really want to look at it. I just want to show you the technique. Okay, so, and it's kind of an introduction in certain ways to chapter 13, where he talks about a generalized linear model, which we may or may not really get to. I haven't put it in the syllabus, though I'd like to touch on it a little bit, if possible, later in the course, so that you won't be missing that. So transformations. To correct model assumptions. The standard model. Correct model assumptions to conform to the standard case model assumptions, which, as we've seen, give you optimal properties for the least squares estimators. The least squares estimators have optimal properties under the standard model assumptions, which is constancy of the error variance. Okay? Okay, there's constancy of the error variance, and of course there's whether the actual model, the linear model fits. So there's a couple of things. So first thing I want to do is, the main thing is transformations to transformations to stabilize the variance. Okay. And this may be a topic that's not familiar to you, and it's going to look a little bit hand-waving to you. So I want to look at example 5.1, page 175 of the text, which has to do with peak energy demand. Peak energy demand of an electric utility. And I'm just going to go through the example. I've got worksheets for the examples, so you can have a look at what's going on. But it's fairly clear from the book what's happening. Okay? So, Okay, so let's have a look at example 5.1, peak energy demand. Save it to the desktop. Okay. Open it. Okay. So let's have a look. What you have here is peak energy demand. That's the dependent variable. And you also have the total demand, okay, for a given day. So there's certain days that I can't remember if they were in July. Let's see. There's certain, no, these are customers. 53 residential customers in August 1979. Okay. And actually that was their peak demand for that customer. Okay. So you have a bunch of customers, and here they are. So there's the customers that use more, and there's the customers who use less. This is the scatter diagram. Right? Okay. So if I go ahead and just go ahead and look at the simple linear regression of y on x. So this is just a one regressive variable problem. Simple linear regression. Look at the residual plot of simple linear regression on the original peak energy usage data. There it is. Predicted value on the horizontal axis. We're going to make it a little bit bigger so you can read it. Okay? And then the residuals on the vertical axis. I think these are the unnormalized residuals. They are not normalized in any way. It's just coming down from this residuals right here. Let's see if that makes sense. Yeah, it looks like it's right. The mean square the standard deviation for error in the simple linear regression is 1.5. Okay. So these are the unnormalized residuals. Okay. So what do you get from that residual plot? What I'm seeing here is kind of this V shape coming out like this. You can't see a full V shape because there's not enough large energy using customers, right? But if they was all kind of filled in, you can imagine this V shape coming like this. Right? Does that make sense? So it looks like variance. If you think of variance as basically the standard deviation is the height there. Okay. So what does that mean? Or maybe not the standard deviation, maybe the variance, but it looks like something's going on, right? We're not sure exactly what's going on. Is the standard deviation going up linearly? Is the variance going up linearly? Or what? Okay, so we're going to actually just guess here. Okay? We're going to make a kind of a heuristic model. Okay? So why is the energy demanded by that customer at the hour of peak usage among the total populace served by the electric? Actually, yeah. So what it is the hour of peak usage. Okay, so demand of that particular customer. Is their demand high? You expect their demand to be high as well, right? But is it a linear function of their own usage for the day? Does that make sense? So you're using a certain amount of energy in the day, and when everybody's using a lot of energy, you expect them to be using that, a lot of energy too, per unit time. But their peak usage, right, that peak hour usage may be higher or lower, than what you might expect it to be. Okay? So there's going to be some fluctuation about any kind of, even if there was a straight line plot, okay? Your peak usage probably is going to be more if you use more energy, okay? So what was it? Here was the scatter plot for original data, peak energy use, okay? Right up here. Okay. So you can see fitting the straight line or something like that. So what do you guess? It looks like the variance isn't constant anyway. Okay. Now what's a heuristic model? Heuristic model is that this is Poisson data, okay? In terms of the number of kilowatt hours, okay? The actual peak energy usage may be viewed as a count of energy units. How many energy units am I going to use? Okay? Am I going to put on 3 air conditioners or 10? How many? So, in some sense, it's the rate at which I'm flipping on the lights and so on and so forth. Okay? So it's kind of it's not easy to justify that heuristic, but we may play with the game that we could think of this energy usage as a Poisson data. Maybe historically it's been viewed as such. Okay. How does Poisson data arise? Well, you can think of it as every light being flipped on, okay, with a small probability, and then how many lights do you have in the house? If it's a gigantic house, it's going to be a total amount of energy is going to be used a lot, okay? A lot of flipping is going to go on, okay? Lights are going to be flipped on, machines are going to be flipped on, and so on, okay? So in a smaller house or smaller apartment, okay, not as many switches to flip, okay? A smaller volume, okay? So you can think of a Poisson random variable as a binomial, okay, of large size and the number of switches being flipped with a small probability P. Small probability P. There's so many switches in a house, you don't turn them all on, right? Okay. So P is a small parameter, N is a large number of switches, okay? And then if I take large N and small p, then this is approximately a Poisson with parameter lambda equals, or mu equals NP. Okay? Approximately. All right. So we can think of the amount of peak energy used as a count of energy units. Okay? We'll pretend it's a Poisson variable. Okay? Now the variance of a Poisson variable is equal to its mean. Okay? So that means the variance would be going up with the mean. Okay? Which may or may not look like what's going on down here, because from this residual plot, that means basically I'd have to be taking a square root for the standard deviation, increase to the standard deviation. Oops, I got the wrong picture. It just looks like you can't tell whether that's linear or square rootish, right? That funnel, you can't tell at all very well. You might think, oh, it looks pretty linear because of these dots along here. That looks like a straight line. Okay? But, this kind of curves down here and so on and so forth. So maybe it's closer to a square root funnel. Okay? Which would mean that the standard deviation is going up as a square root, the variance is going up linear. Okay? Does that make sense? So really have to rely on the heuristic in order to see if there's anything being done here. So this is going to be the model. Okay? Now mu, the mean amount of energy, would of course depend on X, whether you're a small user or a large user, right? Whether your demand is overall small or overall large and so on. Okay? So this we would initially model as a linear function. Okay? As beta 0 plus beta 1x. And then you might, could correct that, perhaps, if you really got into the model. Okay? But what's the variance of this Poisson? The variance of y sub x is therefore also equal to the mean of y sub x equals mu sub x. Okay? So that's not constant because it's going up linearly. Therefore, if this Poisson assumption is true. Okay, so what do you do with that? Okay. Okay, so now I need to do a little bit of math. Okay? Let's talk a little bit about the Poisson distribution and general kind of transformations. What I'm going to do is just apply a little bit of applied math here and see what happens. Okay, so I've got a random variable, y, which I've assumed has a Poisson distribution with mean mu sub x, which I'll later model as this linear function. Okay? And what kind of transformation could I do to get the variance constant? I just want to transform y. Is there something that will do that? If I had a Poisson random variable, what can I do to make its variance constant? Is it possible to do that? In other words, can I transform a Poisson random variable? It turns out there is a good trick, okay, for Poisson data. Okay. If here's the following. Let G of y be a transformation of a random variable y. Then let's see. I'm going to make the following Taylor series. I'm going to write G of y equals G of mu plus G prime of mu. I'm going to center around the mean mu. Okay, G prime of mu times y minus mu. I'm just going to write. So thinking of y just as a real variable. Okay, but then making a Taylor expansion about mu of a function g. So g is not the same as y. G is like, well, f would work too, but I guess we're using g here. All right? G of y equals G of mu plus G prime of mu times y minus mu plus 1/2 G double prime of mu y minus mu squared plus and so on. This is a Taylor series for g expanded about y equals mu. Where mu is going to be the mean of y when we actually apply this method. Okay, so what would I get? I would get the expected value of g of y is equal to g of mu. Take the expected value. Now consider y as a random variable. Okay. Now write y as a random variable, so, make it a bold y if you want. Take it as a random quantity. All right, and I'm going to average over the probability variable. Okay. Okay. G of mu plus G prime of mu. What's the average of y minus mu if mu is the mean? That's 0, right? Plus times 0 plus 1/2 G double prime of mu times what's the average of y minus mu squared? That's the variance of y. Okay, the expected value of y minus mu is the expected value of y minus mu, where mu is the expected value of y. So that's EY minus EY. Right, that comes out to be 0. Plus ... And we're going to, in the applied math version of this derivation, we're just going to skip the ... right? And then worry about it later. Okay? Much later. Never. Okay? Today. All right, we can go back and look at the assumptions we're making. What are we actually trying to do here? But when we actually come up with our G for this example, you can see you could argue that you could successfully throw the other terms away because the higher derivatives are going to get small at mu. Okay? Turns out. So Now, what about the variance? How would I calculate the variance of g of y? That's a little bit harder. If I use the shortcut formula, which would be expected value, let's just do it this way, expected value of g of y squared minus the expected value of g of y, the quantity squared. Then what would I get? So this came out to be approximately equal. The expected value was g of mu plus the correction term involving a second derivative. If I use the shortcut formula, quote-unquote shortcut formula for calculating the variance, which means I take the expectation of the square minus the square of the expectation, I have a formula for the expectation now. All right, I'll plug that in. What's the expectation of the square? What will I do? And I'm only going to take certain terms. All right, I'm only going to take the expectation of the square. So the expectation of g of mu plus g prime of mu plus times y minus mu plus g 1/2 g double prime of mu times y minus mu squared. Let's say approximately this. I'll throw away the plus dot dot dot. Square this, right? And I'm going to throw away some more terms because if anything that's higher order than second order, I'm going to throw away. Minus g of mu plus 1/2 g double prime mu times the variance of y squared. Okay. Okay, go through this calculation. What am I going to save? I'm going to get a bunch of terms here. Some of the terms are going to go out. For example, the cross terms with g mu, g prime of mu times y minus mu, using the fact that the expected value of y is equal to mu, that term will go out. Then I'm going to get an expected value. I'm going to have a cross term between g mu and g double prime of mu, y minus mu squared. Okay, expected value. But that's going to exactly cancel this cross product term when I actually expand this, because there's a corresponding cross product term here. All right, the g of mu squared is going to go out with this g of mu squared. The 1/2 g double prime mu variance of y squared. I'm going to throw it away. Okay, it was too high of order, and anything of order 3 or higher I'm going to throw away, basically. In other words, if it's got a variance of y squared, that's a fourth order term. Okay, so I'm going to worry about this term squared, the cross product term. Okay, from this one, and I'm only going to consider this squared, this squared. I'm only going to consider this term multiplied against that, which I said did cancel. Right? So, so I'm not showing you everything. I'm showing you sort of the device in which what I'm going to throw away, and not telling you why I'm going to throw it away, except that I'm going to say anything third order or higher, I'm throwing away. So that'll give me then what's left is this thing squared, expectation. Okay, so this is approximately equal to g prime of mu squared times the expected value of y minus mu squared. Okay. Okay. So, for example, a second derivative times the variance of y, the quantity squared, is a fourth order term. I just call it a fourth order term. Okay. So what is this? So this is what I get, and this is equal to. I know this seems very cookbookish, but it's better than just what the author says. Is it does work? Period. Okay. At least I'm showing you where some of the arguments come from. Now, okay, that's it. So that's a formula for the variance. So that's actually, which is g prime of mu squared times the variance of y. Okay, so I have an approximation formula for the mean and variance of g of y. Boy, my pen power is getting low here. Okay. That's a good one. Okay. Okay, there's a good one. Now, and actually this formula looks a little bit nicer than this one. But that's okay. All right. So I have this for the mean, and I have that one for that. This is for the mean. I'm actually not going to use that. Okay? And this is for the variance. Variance of g of y. This is called the method of propagation of error in some books. Well, I'm just using this Taylor series to do this. Okay. So, let's just see, I haven't argued that I could throw these things away, but if this Poisson data, we'd make further arguments. Let's just apply it now. Let's see what happens. What function g will make this expression constant in mu? A constant function of mu. The question is, what makes that? That's a differential equation. I've got the variance of y is equal to mu. Okay? That's what I've assumed, because I've assumed the Poisson assumption. So now, if variance of y is approximately equal to mu, all right, then the variance of g of y is equal to g prime of mu squared times mu. All right? And I want that to be a constant. Well, that just becomes a differential equation. Because if I want this equal to a constant, if and only if, let's see, g prime of mu squared is equal to a constant over mu. Okay. And so now I can take a square root, say, so that's dg d mu equals another constant c prime over the square root of mu. Okay, so what function dg dx equals c over the square root of x? What function will do that? What function has a derivative 1 over the square root of x? Square root x has derivative 1 over the square root of x, roughly. So g equals the square root of mu is going to do the job. Solved by g equals the square, g of y equals the square root of y. I'm interchanging the roles of y and mu. So that's the transformation that's going to do the job. I can check it. What would be the variance if it's a Poisson? According to this formula, then that gives, this gives that g prime of y is equal to 1 over 2 square roots of y. And so g prime of y squared times y is equal to 1 over 4y times y equals 1/4. So the variance should be approximately 1/4 if this is correct. Wow. Okay? And when I actually do make the transformation, you'll see right here. Well, you don't see it now because the computer's not on. Okay, I'll show you. Okay. Any questions about this? So I should get something about 1/4 after I take the square root of y. All right? Let's try to regress the square root of y on a simple linear regression function. All right? Beta 0 plus beta 1x. If everything is kosher, I should get that the mean square for error, MS res, should be roughly 1/4. Okay? That'll be kind of a check. All right? To see if everything is going well with this Poisson assumption. And if I do get anything even close to 1/4, like 0.3 or 0.2, I think I'd be kind of happy, for MS res. All right? So, let's have a look. And let's see what happens to the residuals and all that good stuff. All right? So let's see if this is going to do the job. So you can follow the text too. I just have it on the worksheet here. What I'm going to do is I'm going to call y star equal to the square root of y. Here it is. Y star equals the square root of y. So I've added another column. I put the x's again because I want to have the x next to the, I don't know why I wanted to have x next to y star. I guess so I could have the scatter plot. Y star equals the square root of y versus x. Just decided to look at the transformed model there. Okay, see what it looks like. Maybe that looks like more the variability is constant in the vertical direction. Okay? We'll see. All right? So there's these. Does that look more like a linear scatter plot? Okay. Perhaps. So let's go ahead. Let's go ahead and regress y star on x with simple linear regression model. Okay, I've kept the labels. I suggest you go ahead and keep your labels. I've been having a little bit of trouble grading the homework because sometimes people don't put the labels on. I can't track what they actually did with their linear regression analysis. That could be a problem if you did it wrong. Like you put the wrong columns in, somebody did last time. Well, I couldn't tell exactly what happened. I mean, I could tell by, sort of backtracking a little bit, but I wouldn't be able to tell immediately. So keep as much labeling as possible. Just helpful to read. Okay, so here it is. Here's the mean square for error, 0.215. Their estimated mean square for error. That looks about right according to this Poisson assumption, right? That's kind of interesting. It's not a quarter. It's 0.215. I wouldn't expect it to be exactly a quarter anyway. All right. It's just not 0.0215. Okay. So that's kind of magic. And let's see, what do the residuals look like? There are the residuals now. Do they look better? I don't know. Let's see. Let's look at some normal probability. The original residuals didn't look that bad. Okay. And the new residuals don't look that bad. They don't look that great. But for the normal probability plot, but there's pretty much not worse. Maybe there's one outlier now. Okay. But that's a different issue. All right. And then we're not going to study removal of outliers. If we wanted to get into this data, we could do that too. I just want to see if the basic transformation is okay. All right. Those are the residuals. So, pretty much the constancy of variance problem has been solved as far as we're concerned.
When you try and do the normal probability plots, when you're just doing the data regression or the regression thing and data analysis,
yeah. Normal probability plots on Excel do not work. Period. Okay. Period. End of sentence. It's a blown deal.
Yeah.
All right. Sorry, Excel creators, but that's wrong. Okay. Maybe Google will fix it. I hope so. And, there were just a couple little glitches in there. By and large, Excel has been a very serviceable program. You can see that, luckily the authors of this text even put all their data on Excel files already in fast for us to use. All right, it's a nice spreadsheet. So this is good. This is good for an intro course like this. I think it is. And I just hope Google is as easy as this is to use. Hope it's a little bit better. Let's just pray. Because then we can switch to Google. Sorry, Microsoft. Anyway. I'm sure they'll come back with another one. So there you have, it still looks like it might have some curvature in it, but in the residual plot, but it's hard to say. The other one, so this was all based on a visual studies, whether they looked okay or not. All right. So what you get is that, okay, now you might say, well, it's kind of hard to interpret because now I have my beta 0 and my beta 1. Those fit the square root of y. What good is that? Now I know how to predict the square root of your peak usage. Does that mean I know how to predict the peak usage for customer X? Well, you just take the square of the square root, presumably, right? What that'll actually do, since we're assuming that the square root has a normal error, roughly speaking, the center has constant variance. Then if we're really estimating the mean of the square root of y, all right, and if the square root of y has a symmetric distribution, then, which we can argue, all right, the Poisson does not have a symmetric distribution, but the square root of the Poisson has approximately symmetric distribution, okay, with constant variance. Now we'll be, if we square the prediction, then we'll be estimating the median of the distribution of y, okay, not the mean, which is a little bit different. So there's where the author suggests we make a correction, okay. But the idea is that we get estimators that we could have just estimated with the non-constant variance. We still get a beta 0 and a beta 1 hat, right? And so we can estimate the original data with a straight line. We can fit a straight line to this data. I didn't fit the straight line. I didn't show the straight line plot on here. But there'll be a straight line, right? Oops, I can't do that. There'll be a straight line fitting here. And what's going to happen if I use the original regression coefficients, it turns out that the least squares estimation is still unbiased. Okay. It's still going to be unbiased for the betas, assuming that there really is a linear relationship between peak usage, which I assumed there was. Mu x I assumed was linear relationship. Mu x equals beta 0 plus beta 1x. The least squares estimators for the original data, even though it doesn't have constant variance, will still be unbiased for beta 0 and beta 1. Okay, just to have bigger variances than they would if the variance had been constant. So what you're going to get after you take the square root is that you're going to get estimators that have a smaller variability. Okay, here, what's the standard error of the slope under the original data? Well, you can see the standard errors here. See these standard errors? You can bold them just to see what they look like. And then come over here. The coefficients are going to be different. But the standard errors are going to be smaller. Okay. So you're going to have much smaller standard errors over here. Okay. So there's going to be a little bit of bias involved in terms of where you're estimating the mean, but you're going to have stable estimates. Okay. Or stable estimates after the transformation. So stabilizing variance, also stabilizing your estimates. Stabilize, in the sense of the stabilizing variance is making it constant. Okay, so it's two different uses of the word stable. Okay, one is stabilizing, making it constant. The other one is stable estimators means that they have a smaller wiggle. Okay, they're estimating something. All right, they don't change as much. If I go ahead and get a new data set, those numbers are not going to change very much. Okay. So if I go ahead and get a new data set, my estimate of the intercept and the slope after the square root transformation, those are not going to be that much different. Okay, according to this, the standard error. It's 10 to the minus 4 here. Okay, so it's going to change, maybe this will change by 10%. Okay, the coefficient here. Whereas if I take my original estimators of the slope, I guess the slope is not going to change very much, but the intercept would change a lot. Okay, it could change as much as 50%. Okay, in my original one. Anyway, that's the idea. That's the theory. That did I get that right? 10 to the minus 4. 10 to the minus 5. Okay. Are there any comments about that? About the basic technique transforming what this is possible? Okay, it's possible to get to normality. I mean, to get the constant variance assumption. All right. I know it's not perfect world out there. Okay, that's the way statistics is. I mean, there's a lot of approximations and so on. This is how we transform the data set. Let's try another problem. How about the windmill data? That's next. Sometimes we don't need to transform y, we need to just transform x.
Do we have something that is not to transform y on the first example?
What?
Was there something?
Okay, yeah, because the variance wasn't constant. Okay, I look at the scatter plot, so it looked like it was kind of funneling out as well, right?
Right.
And then I looked at the residuals for simple linear regression. I saw, well, okay, the variance not constant. I'm sorry, it's further down. Yes, this one. I looked at the residuals and saw the variance wasn't constant. So that was the basic key. Look at the residuals. Look at the scatter plot, look at the residuals. So a visual approach. You could do numerical things too. In higher dimensions you would be forced to. What's another possibility? Well, you'll see when we get more than one variable. You're going to have something like that on the exam, perhaps, where if you know, you can look at the residuals versus the variables and see if that's giving you a rectangular picture, right? Residuals versus x1, residuals versus x2, residuals versus x3. If you had three regressors. Yeah. Yeah, I think I asked you to do that in one of the problems. I asked you to look at the residuals versus the 3p. Plot the residual versus the regressor xj for each j. Using these plots, can you make a plausible explanation as to why the multiple regression model part A exhibits a lack of fit? Okay. I'm asking you to just go ahead and do a lack of fit statistic on that problem. I think it's based off problem 418. So a lot of these are based off problems in the book. Okay, so let's go. What I want to do next is I want to look at the windmill data. Okay, so that's example 5.2 in the book. I'll just turn this picture off for now, and we'll have a look at that and then take a break. So what we're going to do next is example 5.2. And here, the variance constant doesn't seem to be the problem. The picture is on page 181. Go ahead and zoom in on this before your time runs out here, Nicholas, on the camera. Page 181, the bottom of the page, there's a scatter diagram of the data. Again, it's just a simple linear regression setup. That is, you have one dependent variable, one independent variable. So it looks like the scatter plot is curved. But perhaps that the problem of constancy of variance is not a problem. We didn't actually make a scatter plot of the residuals. If we did, you would see a pattern. I did on the worksheet, and I think maybe they did later in this page. Yeah, there the residuals are on the top of page 184. So they clearly show a pattern, bulge-shaped pattern. Okay, but maybe the variance constant isn't the problem. It's more like the fourth picture there in chapter 4, just the difficulty, which was back there on page 142. They show frame D in what can go wrong with the model, only upside down. These are the residuals, only it's upside down. It's a frowning face instead of a smiling face in your example in the windmill data. All right, so we'll come back to that after the break.